describe measures of central tendency, and then later we're going to talk about measures of variability or dispersion or spread of scores. Central tendency is a statistical measure. It's a single score that's used to define the center of a distribution of scores. And the reason why we use this is to find a single score that's the most typical or best represents the entire group. For each of these distributions, I want you to take a second and look and think, how would you define the center of that distribution? For the first one, it's pretty easy. You can see that 5 is the middle. It's also the most common. It seems to be quite clearly the center of the distribution. But when you look at B, it's a little more complicated because the most common score is 8, but the middle of the distribution doesn't seem to be 8. It seems to be something like 6. But how do you define 6? Because the real center of the distribution is actually 5. If you look at the spread from 1 to 9 and you just picked the middle score, it's actually 5. So it's difficult to say. We have kind of this intuitive sense that the center is maybe around 6 or 7, somewhere in the middle there. But the point is, you can see that the center of this distribution is quite clearly not 8, even though the center of the first distribution was quite clearly 5. For the third distribution, you can see that there's actually 2 peaks. There's a peak at 2 and a peak at 8. And if you took the true middle, it would be 5, but 5 would be a very misleading center of the distribution if you were to use that score and say the middle of the distribution is 5, because nobody even got a 5, and nobody even got close to a 5. I mean, nobody got a 4 or a 6. Most people got either a 2 or an 8. The lesson here is that there's no single concept of central tendency that's always the best. Different distributions require different conceptualizations of what we mean by the center or the middle of a distribution. In each situation, you need to choose the one that best represents the scores of that specific situation. So, for different kinds of distributions, we have different definitions of the center or different measures of central tendency. The first one I'm sure you're familiar with is the mean. There are 3 definitions of the mean. First, you could say it's the sum of the scores divided by the number of scores in the data. This is probably the definition of the mean that you're most familiar with. When you were probably in 3rd or 4th grade, you learned how to compute the mean. You add up all the scores and you divide by how many there are. I'm showing you that same definition here in statistical notation. And the reason why I'm doing that is because it's important that we become familiar with how to articulate common concepts that you're already familiar with in statistical notation. So here you can see this symbol is called mu. Mu, M-U. It's a Greek symbol, and when we use it in statistics, we use it to represent the mean of a population. The mean of a population is equal to the sum of all the scores in the variable x divided by how many there were, the n. So in a population, remember from the first module, we use a capital italicized N to mean the number of people in the population, and X to represent all their scores. So if we add up all the scores and divide by how many there were, that is the population mean. In statistical notation, we use slightly different symbols for a sample. You can see here that we use an italicized capital M for the mean of a sample. And again, we sum them all up, and we divide by how many there were. Remember from Module 1 that the number of scores in a sample is represented by an italicized lowercase n. So the mean is equal to all the scores summed up divided by how many scores there were. You could also define the mean as the amount that each individual would receive when the total of all the things that you're adding up, of all the scores or all the objects or all the whatever it is is divided equally among all the individuals in that set or in the distribution. So imagine for a moment that everybody in a classroom has a certain number of pieces of candy. Everybody has a different number of candy. Some person has 5, some person has 3, another person has 10. If everybody were to pass in their candy, and we were to divide it up into the number of people in the class, and everybody got the same number of pieces of candy, that would be the mean. That seems intuitive, I hope. Also, hopefully not too obtuse or obvious, because at some point later in the term it's going to become valuable to remember or understand that if we were to take the amount that we have and divide it equally across all the people, that every person would get the mean. The third definition is a balance point for the distribution. In this figure, it looks as though we've put a scale together with the balance point represented by mu, the mean, at 5. But how do we pick 5? It's not like the weight of these blocks is evenly balanced across 5, because there's 3 blocks on one side and 2 blocks on the other, so that doesn't make a lot of sense. But what we have done is we've balanced the distances from the balance point, from the particular middle point of the distribution. So I'm going to show you what I mean by drawing. This score right here, this box, is 1 distance away from the mean. This 6 is also 1 distance away from the mean. This 10 is 1, 2, 3, 4, 5 distances away from the mean. If you add up all those distances, there was 5 here, plus another 1, plus another 1. That's a total of 7 distances from the mean. On the other side of the balance, we have 1, 2, 3 distances away from the mean, and 1, 2, 3, 4 distances away from the mean. The total of 3 distances and 4 distances is also 7. And so you can see that the mean is the balance point between the distances away from the scores on the upper side and the lower side. This also will become a concept, an understanding of the mean, that will come in handy as we go later through the term. Now I'd like to take a second and point you to the formula sheet that I've given you for the class. Hopefully you saw my note in Canvas at the start of this module that said, please print out and follow the formula sheet as we go through the work of this chapter, and it will become a close friend as you work through all of the statistics that we run this term. Notice here that the mean, the statistical notation for the mean, is articulated here on the formula sheet in the upper left-hand corner. You have a different computational format for the population versus the sample. As I articulated before, the mean of the population is indicated by the Greek letter mu and the capital letter N, whereas a sample is with a capital letter M and a lowercase letter n. But really, the computation of these two formats, a population and a sample, are actually really the same. They're just indicated with different symbols. Now, at this point, there are a couple of characteristics of the mean that I want to make really clear for you. I'm going to demonstrate these principles in Excel. If you change the value of a score in a set or in a sample, it will change the mean. If you introduce a new score or remove a score, that will change the mean, unless the score that you add or remove is already exactly equal to the mean, and then it won't change anything. If you add or subtract a constant from each of the scores in a set, then that will change the mean by that same constant. If you multiply or divide each of the scores by a constant, then that will multiply or divide the mean by that same constant as well. So as I said, I want to articulate these very clearly in Excel for you. So first, we have an original set of scores. These scores range from, it looks like, a low of 5 up to a high of 20. And you can see that the mean is computed here as 13. Now, this is a set of scores that is exactly the same as the first, but here I'm going to take one of the scores and change it and see what happens to the mean. So if I take, say, this 20 right here, and I change it to 25, then the mean will change as well. If I add a score to this sample here, that will change the mean as well. So down here in this blank spot, I will add a score of, say, 17. That will change the mean. If I remove a score, say I take away this 9, that will change the mean. If I add or remove a score that's equal to the mean, like if I take out this 13, the mean does not change. If I add in a 13, the mean does not change. And remember, the reason why this is because the mean is the balance point. If you imagine that scale once more that we talked about on a couple slides ago, and you keep placing scores on top of the balance point, it doesn't shift the balance at all. All it does is keeps adding scores right on top of the fulcrum. And as you do that, you can add an infinite number of scores, and it's not going to change the mean as long as they're exactly on the balance point. Now, if I add or subtract a constant to each of the scores in this distribution, then it will change the mean by that same constant. So instead of having this be equal to 12, I'm going to make this cell equal to the original plus 4. And I'm going to carry that through to all of the other scores in the distribution. And you're going to see that the mean changed to be 13 plus 4, or 17, as well. I could do the same by subtracting an amount. If I did equals the original value minus some amount, say 7, then the mean, once I carry this formula throughout the rest of the set, the mean will be 13 minus 7, or 6. I could also multiply or divide each of these values by a constant. If I took the original and I multiplied it by 2 and carried that formula throughout the entire distribution, then the mean would also be multiplied by 2. 13 times 2 is 26. Or if I divided it by some amount, if I made the original score divided by 3, say, and then I carried that value through the rest of the distribution, we would see that the mean would also be divided by 3. So whatever you do to the mean, whatever you do to individual scores in a distribution by way of multiplying or dividing, the same will happen to the mean. The next measure of central tendency, which I hope you are also familiar with, is the median. The median is the midpoint of the scores in a distribution when they're listed in order from the smallest to largest. The median divides the scores into two groups of equal size. It puts scores in order. In order to compute it, you put the scores in order and identify the middle score to find the median. So if you have the scores 5, 8, 11, 10, and 3, you would have to reorder them into 3, 5, 8, 10, and 11, because this is from smallest to largest. And then you just choose the middle score. So the middle of this set of 5 is 8, and that is the median of the distribution. In order to locate the median in a distribution of scores where it's an even number and there isn't a middle score, you just find the middle two scores and you find the arithmetic mean, or the average of those two. So you add together 4 and 5, divide by 2, and the median is 4.5. The median and mean are two different definitions of the center, or the middle, of a distribution of scores. The mean is the balance point of the distribution, as defined by distances, but it's often not the midpoint of the scores. The median, on the other hand, is the midpoint of a distribution, as defined by the number of scores, but it's often not the balance point of the scores. So in any given sample of scores, you're often going to find that the median and mean are different. but they both give you helpful information about understanding what the center or the middle of the distribution is. So in this case, in the example shown here, if we were to list out all the scores, you've got 3 2s, 2 3s, and a 12. 2 2 2, 3 3, and 12. The median of this distribution is between the scores of 2 and 3 because it's an even number of scores. So the median is 2.5. But the mean, if you add up all these scores and divide by 6, is 4. So you can see that the mean and the median aren't different, but the mean is more reflective of the distances. It's the balance point in terms of distances away from this mean here. The median, though, is the middle of the distribution as defined by the number of scores. So 3 scores fall below the median and 3 scores fall above the median. The final measure of central tendency that we're going to talk about in this class is the mode. The mode is the score or category that has the greatest frequency of any score in the frequency distribution. You can use this with any scale of measurement, which is a real interesting plus. Specifically, and importantly, you can use it with nominal or ordinal variables. You remember from the first module when we talked about nominal variables being those that are categorical, like how did you hear about our store? Through a newspaper ad or a TV ad or a banner or something like that. Those categories can still, you can still find the center of a distribution by the quote-unquote center, by the most common of those categories. This also has a benefit of always corresponding to an actual score in the data. I'm going to go back one slide to show this, so you can see that in the case of the median, which is 2.5, nobody actually scored that. In the case of the mean, which is 4, nobody scored that. But when you're looking at the mode, somebody necessarily had to have said, in fact, most people will have said that value. And so in this distribution here, the mode is 8. It's the most common value that was obtained. And 4 people got that value. So it will always correspond to some actual person's score in the data set. You can have what are called bimodal distributions. A bimodal distribution is one that has multiple modes or multiple peaks. You can call a distribution bimodal even if the 2 modes aren't actually true modes. Like 2 is the true mode of this data set. 8 people got a 2. Only 7 people got a 10. But because of the shape of the distribution, you could consider that 2 and 10 are both modes because they're both peaks of this bimodal distribution. The mean, median, and mode will differ depending on the type of distribution you're working with. In the case of symmetrical distributions, the mean and median will always have the same value. And if there's only one mode, as you see in this first figure here, then it will also have the same value as the mean and the median. But in a bimodal distribution, the mean and median will be in the center, but the modes will be different. A distribution may have more than one mode, or no mode at all. So as you see here, there's multiple modes, but here there's no mode because all of the scores had an equal percentage of people responding to that value. In each of these cases, because they're symmetrical, the mean and median fall exactly in the center of the distribution and are the same value. However, when you have skewed distributions, the mean is influenced more heavily by extreme scores, which are found far toward the long tail, either in the positive or the negative direction. But the median, in order to divide the scores in half, is actually found toward the long tail, but not quite as far as the mean is. So in this skewed distribution here, you can see that the mean is pulled toward the outliers. It's more heavily influenced by the outliers than is the median. And the mode is found near the short tail. It remains at the peak, so it's almost entirely uninfluenced by outliers. You can see the same thing in this case with a negatively skewed distribution. The mean is pulled most far toward the tail, towards the outliers. It's most heavily influenced by the outliers, whereas the median less so, and the mode is still at the peak. Because of these characteristics, it's important that you understand the shape of your data before you select a measure of central tendency. For instance, you should use the mean whenever you can. Especially, you should use it if you can calculate the sum of the scores, and you know the value of every score. But that's not always the case in statistics. Sometimes you have extreme scores or skewed distributions, undetermined values or open-ended distributions, ordinal scales, nominal scales, and if you have any of these situations, it's misleading to compute the mean. Let me explain why. In the case of extreme scores, remember, the mean is most heavily influenced by outliers, and so a mean could look artificially high or low based on one very extreme value. In the case of a skewed distribution, it's a very similar situation where multiple extreme scores are skewing your distribution, and so those are pulling over the mean toward their extreme values. Undetermined values would be like, say if you were in a NASCAR race and a car didn't finish, so it doesn't have a particular time associated with its finishing the race. That would be an undetermined value. You don't have a time because it didn't actually achieve the end of the task. So that's an undetermined score, and you can't compute the mean if you have a score that's undetermined. If you have an open-ended distribution, like say you ask a survey question that says, how many children do you have? 1, 2, 3, or 4 plus. That open-ended category means that it's grouping together a bunch of people who have 4 children, or 7 children, or 12 children, all together as if they had the same number of children. And that can be misleading. If you have an ordinal or a nominal scale, these are categories. You can't compute the average of cats and dogs because those two things are separate individual categories. They're not on a continuum. If you can't compute the mean, then the next best measure of central tendency ordinarily is the median. You would use the median in cases where you have extreme scores or skewed distributions or undetermined values or open-ended distributions, but not if you have nominal scales, because you can't compute the median, the middle, of cats and dogs either. The mode is the only measure of central tendency that can be used with nominal scales, because you can have a category that scored the highest value. So, like, if you have a distribution of kinds of pets, and some people said turtles, and some people said ferrets, and some people said dogs and cats, then one of those categories, I would assume dogs, but maybe cats, I don't know, would be the highest scoring proportion, and that would be the mode. And even though they're categories, you can still compute the mode from that distribution. You should also use it if you have discrete variables, or in order to describe a shape, like a bimodal distribution. But if you can compute the median or mean because you have interval or ratio data, then you should not compute the mode and report that as your only measure of central tendency. It is fine if you accompany the mean or the median with the mode, then it's fine to include that, but you should not use the mode as your only measure of central tendency if you can compute the mean or median, because those are better values. Throughout this course, almost all of the statistics that we're going to be using will rely on the mean. But the mean is biased when you have an outlier, and so we have to be cautious that whenever we run inferential statistics, from now on through the rest of the course, that we recognize that our outliers might be unduly influencing the conclusions that we're drawing. So in this case, what your mean is going to be from a set of scores that are ranging from 10 to 13, but where one person scored 100, this score right here is going to unduly influence the mean so that it's much higher than the actual bulk of the scores down here between 10 and 13. When you have an outlier, there are a few best practices to deal with it. You might run your statistics with the outlier included and then remove the outlier and run it again without it, and report your statistics both ways and say, here are the conclusions we would draw if we included the outlier, and here are the conclusions we would draw if we didn't. Another approach might be to fence the outlier, where you take the outlier and you say, I'm going to bring it in to a certain defined amount above the mean. So, above the median. So if I took the median of these scores here, it would be 11.5, and I might say, okay, we're going to go, we'll talk about this again in a later module, but I might go 1.5 interquartile ranges above 11.5, and I might cap the most, the highest possible outlier at, say, like 16 or 17, something like that, and I would artificially change this score from 100 and bring it down to 17. And even though I know that this person didn't actually score 17 or 20 or whatever it is I'm going to fence it in at, I'm making an like an outer boundary where I'm going to say no person is allowed to score higher than this value of whatever it is, 20 or 25 or 17 or whatever it is. I'm going to say that's the highest possible score I'm going to allow anybody to get. And even though somebody scored much higher than that, I'm going to allow this score to still retain its extremeness. It's way higher than the other scores in the distribution, but if I fence it in, if I bring it into the boundary, that fence that I've created, then it's not going to shift the mean of the whole distribution so far out that I can't trust any of my statistics. What I don't want to do is just remove the outlier from the data set. Sometimes statisticians or researchers will do that, but ordinarily, if a person actually achieved that score, if they actually got it on whatever scale you're measuring, you shouldn't just throw it out because it represents a real person. It represents a real possibility. And even if they're very different from everybody else, it doesn't mean that it's not true. Now, if you get an extreme outlier, it's probably best that you do double check and make sure that really, in fact, the outlier is a valid, is a valid outcome. Because if you double check and you notice, oh, this is just a typo, like somebody accidentally put an extra 0 at the end, but this is really supposed to be a score of 10, well, then you wouldn't want to fence it. That would be an inappropriate thing to do. You'd want to fix it to make it represent the actual value that somebody got, and that would be 10. But if it really was a legitimate score that somebody got, then you wouldn't want to change it to 10, and you wouldn't want to just throw it out as if that person was an invalid person. If somebody could actually achieve that score, then you should allow that score to still be in your data set, but you might run the statistic both ways and report it with and without that outlier, so you have kind of like a measure of how much that outlier is influencing your data set. Or you might fence the outlier to some extreme amount, allow it to retain a level of extremeness, but not so much that it throws out the conclusions we could draw. Now, before we continue with the measures of dispersion or variability, I'd like you to take a moment and practice understanding which measure of central tendency should be employed for understanding for capturing the middle of each of these distributions. I'm going to have you pause your video for a second here and decide whether the mean, median, or mode would be best for each of these distributions. For the first one, the number of people born each month of the year, there is no mode, so you couldn't compute that. The mean and the median could be computed, and they would be the center of this distribution. But in actuality, just describing this distribution here with a mean or a median isn't going to give you a very clear understanding. Using other kinds of words that statisticians might describe, might use to describe a distribution with, might be a better approach for this distribution. For instance, if you say that the data are uniformly distributed, in other words, they are they are the same across the entire distribution, then using that word, uniform distribution, would be a better way of articulating this than to say that just the mean or the median, because that would give a false impression of how the data look. The GPA of students at Central Washington University would probably be best represented by the median. Remember, if you can compute the median or the mean, then you don't want to use the mode as your sole representation of the data. So the median would be pulled towards the outliers this direction and might appear somewhere like right here. The mean would be pulled towards the outliers but would appear somewhere closer to out here. And those GPA scores wouldn't accurately reflect what students, the bulk of students, are really getting. So in a skewed distribution, the median is the best measure of central tendency. The height of students at Central Washington University is a normal, symmetrical distribution, and so the mean, median, and mode will all be the same. You can use any of them, but if you can, then you should use the mean. Indeed, throughout the rest of our term, we're going to use the mean to describe most of our distributions whenever we can. And all of our statistics will depend on our ability to compute the mean. So we're assuming throughout the rest of the term that most of our data are distributed in a normal way like this. And if they are skewed, we have to go through cautionary measures and corrections to our statistic to kind of see what kind of influence those outliers will have had on the conclusions that we're drawing. The starting salaries of new graduates from CWU is positively skewed. So again, in a skewed distribution, you're going to want to use the median as a measure of central tendency. It is influenced by outliers, but not so much as the mean is. And finally, the number of people eating at a steakhouse throughout the day, which is what we talked about in our last module, you can see that it's a bimodal distribution. And so to describe the mean or the median here at the center is a little bit misleading. It would be more accurate to say that you've got modes at 12 o'clock and 7 p.m. or 6 p.m. or whatever that is. Okay, the next category of statistics that I want to talk about are measures of variability. Variability can be defined in a couple different ways. One way is to say it's a quantitative distance measure that's based on differences between scores. It also describes distance of the spread of scores, or distance of a score from the mean. I want you to think for a moment about the word variability. Like the word variable, it suggests that there are differences across people, that scores vary. They are variable. Variability is a measure of how different they are from each other, how variable they are. So again, I read, a quantitative distance measure that's based on the differences between scores. It's measuring how far apart, how distant measures are from scores are from each other, based on how different they are from each other. The purpose of measuring variability is to describe the shape of a distribution using more than just a measure of central tendency. It can measure how well the measure of central tendency represents the distribution. So in the case of this first distribution here, the center is 70, but the spread of scores is relatively tight around that mean of 70. So because the variability is low and the scores are not that different from each other, most people will score around 70. That measure of central tendency is going to accurately reflect most people's scores. You have some people scoring a bit lower than 70, some a bit higher, but most of the scores are around 70. However, as you can see in this distribution, the scores are more widely spread. 170 is the average, but the distances around 170 are much wider, and so some people will weigh much more than 170, some people will weigh much less than 170, but 170 is not going to accurately represent what most people weigh because these scores are so variable, or because the variability is so spread out around that center of the distribution. We have three ways of measuring variability. The first is called the range, the second is the variance, and the third is the standard deviation. The range, I think you're familiar with. I remember learning about the range first when I was in 3rd or 4th grade. It's the distance that's covered by the scores in a distribution. You just take the smallest value and the largest value and subtract the difference. So, in a set of scores that are 3, 6, 9, and 14, the range is the highest number minus the lowest number, 14 minus 3, or 11. That's the total spread of scores. But this measure is just based on 2 scores, not all the data. So it's a very imprecise and unreliable measure of variability. Let me show you why the range sucks. These 2 graphs have the same range. But, as you can see in the first histogram, the bulk of the numbers are clustered a lot closer around the mean than they are here, where variability is much higher and they're more spread out. The range alone would tell you that these 2 distributions are about the same spread, that have the same variability, or the same spread degree of spread apart. Therefore, we need a different measure of variability. We could start with this statistic called variance. Consider these scores: 12, 8, 10, 10, 8, and 12, versus 28, 4, 6, 4, 2, and 16. The mean of this and this are the same. It's 10 in both cases. But as you can see, there's a way greater difference between the numbers in the second set than the first set of data. These numbers mostly cluster around the value 10. These are way spread apart from 10. We represent this difference using the statistics called variance and standard deviation. The standard deviation and variance for a population are pretty straightforward. The most common and most important measure of variability is the standard deviation. This is a measure of the standard or typical distance from the mean. It's called the standard deviation because it is the standard or typical amount that scores deviate from the mean. Standard deviation. This describes whether the scores are clustered closely around the mean or if they're widely scattered. If you have a low standard deviation, that means that the deviation typically, or in a standard way, will be very small or close to the center. If you have a high standard deviation, that means the scores will be very spread out. They will deviate from the center a lot more on average. The calculation for these 2 statistics, the standard deviation and variance, will differ for populations versus samples. And I'm going to show you how those differ, but first I'm just going to show you how it's computed for a population. And then later on we'll introduce a minor correction for samples. Variance is a necessary companion concept to a standard deviation, but that's not quite the same concept as a standard deviation. In fact, you compute the variance along the way while you're computing the standard deviation. In order to define the standard deviation, we wish we could just compute what we would consider to be the average deviation. If you were computing the average deviation, you would determine the deviation of each person from the mean. That would be to take their score minus the mean of that set of scores. In this example, you can see the scores 3, 4, 4, 5, 7, 7 have a mean of 5. In order to compute the deviation for each person, you would just take their score minus the mean of 5. So 3 minus 5 is negative 2. 4 minus 5 is negative 1, and so on. And the second step of finding the average deviation would just be to add up the deviations and divide by how many there are. In other words, you'd find the average of these scores. Problematically, however, there's a couple of issues. Deviations always sum to 0 because the mean is the balance point. And they're always the same distance on the upper side and the lower side from the mean. So the distances away from the mean on the negative side and the positive side will always balance out, and the deviations will always sum to 0. Then, if you try to take the average of the deviations, it's always going to be 0 divided by how many ever there are. In this case, there are 6 scores. 0 divided by 6 is still 0. It's always going to equal 0. So the average deviation is not a measure that we can actually compute. That means we need a new strategy. So, we fix our second step by removing negative deviations. Now, if you think about this, there are a couple of ways we could do this, but one of them works especially well in particular. If you square values, then you can get rid of the negatives. For instance, -2 times -2 becomes positive 4. The negatives erase when you multiply two negatives with each other. So to take -2 and square it is a positive value. That removes the negative deviations. So we first square each deviation score, and then we sum the squared deviations. So in that same example that I was showing you before, you've got this set of scores with a mean of 5. You compute how far each person is from the mean by subtracting the mean from their value. This person is 2 less than the mean. This person is 1 less than the mean. This person is exactly at the mean. There's no difference. This person is 2 above the mean. 2 above the mean. And once you square those values, then you have 4, 1, 1, 0, 4, and 4. No negative values. So you can actually take the average here of these by summing them up. That's called the sum of the squared deviations, sum of squares, and dividing it by how many scores there were. So if you take this, this value right here, that's 14, and you divide it by 6, that equals 2.33. That is the average variability. Now I'd like to go back and define a couple of new terms that we haven't been exposed to before. The average of the squared deviations is known as variance. So if you take these squared deviations and you average them by adding them all up and dividing by how many there are, that's called variance. So in this case, the variance is 2.33. But this value has not been corrected for the squaring we did before. We took each of these values and we squared it. That still is in squared form. So the variability is measured in squared units. By way of analogy, you might compare this process to a magic trick where you need to thread a needle, but the needle head is too small. You just try and try, you can't get the thread to go through the head of the needle. So you call on your fairy godmother to come and magically make this needle much larger than it is. This way, you could shove your whole fist with the thread through the head of the needle and just drop the thread on the other side. It'd be super easy if the head of the needle were expanded a large degree. But if your needle is stuck in this expanded, larger form, then it becomes very unuseful. You can't sew a button if the needle is bigger than the hole of the button that you're trying to sew. And so, at the end of this process, you need to shrink the needle back down once it's threaded with the thread through the head of the needle, but the needle shrunk back down. To carry that analogy through, in order to complete the process of computing your standard deviation, you have to reverse the squares that you performed before. So, the goal is to compute a measure of the standard or typical distances of the score from the mean. The variance measures the average distance of the scores from the mean in squared units. That's not quite our goal. So in order to adjust for having already squared the differences, we have to take the square root of the variance. So the standard deviation is to take that last value we landed at and take the square root of it to shrink the needle back down, or to shrink the standard deviation back down into, or I guess it's to shrink the variance back down into something that's in the original units that we were working with. So once we take the square root of this value, 1.53 is an accurate representation of typically how far the distances of each of these people here are from the mean of their whole set. If you look at the deviation scores, you can see that that's pretty accurate. -2, -1, -1, 0, 2, and 2. The typical distance away is about 1.5 points away from the mean. Some people are a little higher than that. This person is 2 points away. This person is 2 points away. So they're a little higher than that. But some people are less than that. Like these people are 1 point away. This person isn't any points away. So a typical distance away from the mean would make sense to be 1.53. This figure demonstrates the overall process by which we decided to compute the standard deviation in the way we did. Our goal is to find the deviation, or the distance from the mean, for each score. Then you add the deviations and compute the average. Shoot. If you don't square it, then they always value at 0, and so that's a dead end. We created an alternate path by which we squared each deviation, then found the average of the squared deviations, which is called variance, and then we took the square root of the variance to shrink it back down to size, and that's known as the standard deviation, or in other words, the standard distance that each score is from the mean. Let's walk through another example. Here we have a set of scores. There are 5 scores here. The sum of these scores is 1 plus 9 plus 5 plus 8 plus 7, or 30. The average is the sum of them divided by 5, or 6. The next step is what? To subtract the mean of the set of scores from each of the scores themselves to see how far away that score is from the average. We take the deviation scores here by subtracting 1 minus 6, or -5, 9 minus 6, or 3, -1, 2, 1. The next step is what? To square them. So we square the deviations. -5 times -5 is 25. 3 squared, 9. -1 squared, 1. 2 squared, 4. 1 squared, 1. The next step is to add them all up and divide by how many there are. To add 25, 9, 1, 4, and 1, we get 40. To take the average of them, we divide by 5. 40 divided by 5 is 8. The standard deviation is known as the variance, this average value here, square rooted. So the square root of 8 is 2.83. That's our standard deviation. In this example, given this distribution, the standard deviation seems a sensible value. The highest value away from the mean is 5. The lowest value away is 1. So you would expect for the typical distance away to be somewhere between 5 and 1. And 2.83 is pretty close to the middle between 5 and 1. And if you look at the spread of the scores, you can see that a couple scores are just 1 distance away from the mean, a couple are 2 distances or 3 distances away from the mean, and 1 is 5. So you would expect that the standard, the typical distance, would be somewhere in the middle there. 2.83 is a reasonable value. The formula for computing the variance is the sum of squared deviations divided by the number of scores. The sum of squares is abbreviated as SS, sum of squares. It stands for the sum of the squared deviations of the scores from the mean. This is what we've been doing for a few slides now. Remember, what we're doing is we're taking the mean, subtracting the mean from each individual score to find how far away the person is from the mean, then squaring that value. That squared value is the deviation score squared. To sum them up is the sum of the squares. There are two formulas for computing the sum of squares. The fact that we have two formulas could produce some confusion. After you learn the definition of the sum of squares and practice using it in a few very simple sets of numbers, you should mostly stop using it. Because this definitional formula that we've been walking through so far is helpful for understanding what we're doing, but it's really time-consuming and error-prone due to rounding when we're analyzing real data. So after we learn this concept, we're going to shift to using this computational formula, which makes things quite a bit faster to compute, as well as quite a bit more accurate. So, the definitional formula is what we've been doing so far. We find each deviation score, x minus the mean. We square each deviation score, x minus the mean squared, and then we sum up all of those squared deviations. In statistical notation, you can see the sum of squares is equal to adding up all of the x minus mean deviation scores squared. So, if you follow your PEMDAS, the order of following things here is everything in parentheses first. You take each score minus the mean first, then you square each one, then you add them up. That's the sum of squares. The computational formula, like I said, is much faster and more accurate. And so once you understand this concept, and you walk through it a few times, you should start using this formula instead. Here, we take the sum of all the x squareds minus all the sum of x's squared divided by n. Make sure that you remember in PEMDAS that the subtraction comes last. So what we have to do is, in parentheses first, we sum up all the x's. Whatever that value is, we square it. Then we divide by the n, the number of scores there are. Finally, penultimately, we sum the x squared. So we square each score, we sum that list, and then we take this value minus this value. I'll walk you through an example. Here is a list of scores. If you add up all these scores, the sum of the x is 335. Here is a list of all the x's squared. If I square 52.4, it's 2745.8. If I follow that through all the way down the list, I could sum up the x squareds and get 16,147.2. If we were to plug these values into this formula, you would see that the sum of x here is 335, which we would square. The number of scores is 7, and the sum of x squared is the adding up of all of these x squared values. So if we plug those in, you would see we get 16,147.2 minus 335 squared over 7. 335 squared is 112,000. You divide that by 7, and then you take 16,147 minus 16,032. The sum of squares in this case is 115.1. This computation is much faster and easier than it would be to take 52.4 minus the mean of this set, squared, add them up, divide by how many there are, take the square root. That's a very long, drawn-out process that could be just done in a simple formula. But when you're using this formula, you have to use caution, because a lot of students will get confused and think that the sum of squares is the sum of x squared. It's not. Sometimes they'll think it's the sum of x squared. It's not. They also might sometimes think that the sum of x squared and the sum of x squared are the same, but those are not. You have to be cautious not to flip these around. You have to be cautious not to misuse the formula, not to forget that this whole formula is the sum of squares and not some part of it. The population variance is indicated by a formula that I'm going to teach you in statistical notation. Variance for the population is the sum of squares over n, and the standard deviation is equal to the square root of the variance. Again, we've already gone through this, but this is not statistical notation. There are some symbols that we use in order to articulate this more clearly and simply. We identify the standard deviation with a lowercase Greek letter sigma that looks like this, because sigma sounds like standard deviation. Okay, that's not really the reason, but that might be a useful way of remembering. So this symbol right here, sigma, stands for the standard deviation. It's equal to the square root of the variance. Variance being sum of squares over n. The variance is the standard deviation, still in squared form, so we identify the population variance with a lowercase Greek letter sigma squared. So when we write the formula for the variance, we write the sigma squared like that to represent that it's the standard deviation still in squared form. That's equal to the sum of squares over n. If you take the square root of both sides, then the standard deviation is the square root of the variance. I want you to take a moment and just make sure that you're understanding properly by writing a brief description of what is measured by the standard deviation and what's measured by the variance. Go ahead and get out a scrap of paper, jot something down, pause your video, and we'll move on in a moment. The standard deviation measures the standard distance of scores from the mean. It measures the typical distance of scores from the mean. How far away a typical score usually is from the mean. The variance measures the average squared distance from the mean. It's the same as the standard deviation, but still in squared form. By way of analogy, you've got the needle that you've blown up so that you can put the thread through, but you haven't shrunk it back down yet. The variance is the same as the standard deviation, but still in its expanded squared form. I want to point you to the formula sheet and remind you that the sum of squares, the variance, and the standard deviation are all here in this left margin, or in this left column. We so far have gone through the definitional and computational formulas of the sum of squares. And we've walked through the variance formula for populations and the standard deviation formula for populations. In a little bit, we'll get to how we compute the samples as a slightly different computation. The standard deviation and variance for a sample have to be computed slightly differently from that of a population. Here's why. The goal of inferential statistics is to draw conclusions about the population. We draw samples so that we can say something about the population from which that sample was drawn. The samples are based on limited information. Inferential statistics are based on limited information from the sample. Samples differ from the population. They have less variability. If I show you this this population of scores here, with each box representing one person's score, I could draw from this population a sample of just 10 people. It would look like this. Upon removing those 10 people, I would show that the variability of the sample spreads from here to here. Now, that's just the range rather than the standard deviation, but the point is still clear that the sample's variability is restricted compared to the population's variability, which ranges from here all the way up to here. The reason why this happens is because most of the scores in the population are somewhere near the mean. If you try and draw random samples from this whole set of the population, you're mostly going to get scores that are around the mean. You're very, very, very infrequently going to get scores that are from out here in the tails of the distribution. And so the spread of scores in your sample are going to be less than the spread of scores in the population. Computing the variance and standard deviation in the same way for a sample as for a population would give us a biased estimate of the population's variability. For that reason, we have to make a correction. But luckily, the bias in the sample's variability is consistent and it's predictable, so we can correct our estimates for that predictable, consistent, restricted variability. The sample variance and standard deviation is computed very similar. The sum of squares is identical to before, but the formula for variance has n minus 1 rather than n in the denominator. So when you're using a sample, you use the lowercase n for the number of people in your sample, and you subtract 1. We also change the sigma into an s to stand for standard deviation. This formula right here is standard deviation squared, also known as variance. So the formula for variance is s squared equals the sum of squares over n minus 1. And the standard deviation is known as italicized lowercase s equals the square root of the variance, ss over n minus 1. If we compare a population standard deviation and a sample standard deviation, you will see that the computation results in different results. For a population, if you had a sum of squares of 48 and you had 8 scores, you could compute the the standard deviation like this. The square root of 48 over 8 equals 2.45. If it was a sample of scores, however, and you had only 8 scores in your sample, you would take that 48 divided by 8 minus 1 instead of 8 and get a different standard deviation. Now I want you to think for a second, why did the standard deviation increase when we used n minus 1 for the denominator? The denominator is less, but the standard deviation increased. Why? Pause your video if you need to for a second. Imagine for a moment that you're cutting a pizza into a certain number of slices, say 8 slices. You would have each slice be a particular size. Now take the same pizza and instead cut it into 7 slices, 8 minus 1, 7 slices. Each piece is a little bigger than it was before because you're dividing that pizza, into fewer slices. So the standard deviation is going to be reflecting a larger value in a sample. It's important that we understand what we've done here by reducing the denominator is to inflate the variability. Thinking back a couple of slides to when I showed you the sample out of the population, recall here that the sample variability is restricted. It's less than the population variability. So by dividing our formula by n minus 1, what we've done is we've artificially inflated our estimate of the variability so that it's larger than it is really here, and we estimate it to be bigger, wider than it really is, so that it better approximates the population variability, which is bigger and wider. This process of dividing by n minus 1 is known as degrees of freedom. We have to do this because population variance, when you compute it, is just understood as, like, the mean is whatever it is. When you compute the mean of a population, the mean just is what it is. And deviations from that mean on the part of individual scores are computed from that known mean. We know the population mean, and we're figuring out how far is every score from the real population mean. But when we compute sample variance, it's an estimate of population variance. We're trying to figure out how far are scores typically from the population average based on how far apart they are from the mean of our sample. The population mean is unknown when we draw a sample. Using a sample mean restricts the variability compared to the population, and once we calculate the mean of the sample, it fixes at least one score value in the sample. That score, it's no longer free to vary. I'll show you what I mean on the next slide. We use degrees of freedom to make our correction between the sample and the population. So the number of scores in the sample that are independent and free to vary is what we use to divide as the bottom of our denominator. We are using, like I said, n minus 1, but from now on we're going to call this degrees of freedom. And degrees of freedom is n minus 1 when we're calculating variance, but in future statistics you might find that the degrees of freedom is something different, like n minus 2 or something like that. But here, when we're computing variance, it's n minus 1. Let's walk through an example of why the degrees of freedom is n, the number of in our sample, minus 1. Let's say that you draw a sample of n of 3 from a population, and the mean of that sample of scores is 5. If one of the scores is 2, what are the other two scores? They could be literally anything as long as they add up to 13. Like, one could be 10 and one could be 3, or one could be 13 and 1 0, 1 8 and 5, 1 7 and 6, 1 26 and negative 13, or one could be 1,013,000 and the other could be negative 1,000,000. As long as they add up to 13, these two scores could be anything, and this sample will still have an average of 5. So, are these two scores free to be anything they want? In other words, is each one free to vary? Yes. But let's plug in a value here for the second score, and let's say this was a 9. Then what does this score have to be? It necessarily must be 4. Can it be anything it wants? In other words, is it free to vary? No. So the number of scores in our sample that are free to vary once we've computed the mean as 5 is just how many scores we have minus 1. The last one is not free to vary. Once we know 2 of the 3, the last one is fixed. It necessarily must be 4. It cannot be anything at once. And so our degrees of freedom are however many we have in the sample minus the last one. When you have a sample, all but the last score are free to vary, so we say that the sample has n minus 1 degrees of freedom. When you're trying to show or depict the mean and standard deviation in a graph form, it's easy to do that. When showing the mean, we use a vertical line in the center. And when showing the standard deviation, we show a horizontal line to the right. Sometimes to the left or both, but usually to the right. This shows the standard deviation. So in a distribution of scores that are normal, like this, the mean might be shown as 80, depicted by a line in the center of the distribution, and the standard deviation is shown by how far this line goes across. This line, represented to the right, is 8 units across. That means this place right here on the x-axis is 88. And a place that's right here on the x-axis on this side is about 72. On this sample graph of scores, you can see that the mean is denoted by capital italicized M instead of the mu that we saw in the population, but the mean is still denoted by a vertical line at the location of the mean, and the standard deviation is still denoted by a horizontal line that goes in this case to the right and to the left of the mean, and is shown as the lowercase italicized s for standard deviation being equal to 2. Sample variance is an unbiased statistic when we compute it using degrees of freedom, or n-1. How do we know that? Because if we take the average value of this statistic, it's equal to the parameter. I know that's a confusing statement because there's a lot of unfamiliar terms here. Remember back to Module 1, where we described a parameter as being the population statistic. The average value of this statistic, meaning the one we compute from our sample, will be equal to the population's value if we compute it in this unbiased way. I'm going to explain again. The average value of the statistic, meaning if you were to take sample after sample after sample after sample and compute the standard deviation over and over and over on sample after sample, and then you averaged them all together, the average value of all of those statistics that you're computing from sample after sample after sample would be equal to the actual value of the population's parameter for variability, or standard deviation. And so we can say that this is an unbiased statistic because when we take the average value of all the statistics that we've computed from all the different samples, and we look at what they typically are on average, that will be equal to the actual amount that the standard deviation is in the population. A sample statistic is biased if it systematically overestimates or underestimates the population parameter. In other words, if the average of the statistics is not equal to the parameter. I'm going to show you what I mean by average of the statistics using this online resource. Here we have a population distribution. These are all the possible scores that we could draw in a sample. Now I'm going to draw one sample of 5 individuals. That's shown here by n equals 5. Please ignore the fact that this is a capital N. Like I said before, some resources don't use a lowercase n to represent samples, but this right here is a sample of 5. I'm going to animate the process of drawing the sample of 5 from the population. 1, 2, 3, 4, 5 scores were drawn from the population, and the average of those scores is computed. The average of those 5 scores was plotted here. I'm going to draw another sample of 5. 1, 2, 3, 4, 5. These 5 scores have the same average, and it's plotted there. Let's draw another sample. 1, 2, 3, 4, 5. Those 5 scores had an average plotted there. 1, 2, 3, 4, 5. This is another sample. We've computed the average once again, and we've plotted it there. If we do this over and over again, and plot the means over and over again, you can eventually begin to develop a distribution of the sample means. If I do this 10,000 times by clicking this button, and it just does it rapidly without animating them all, we come up with a distribution down here that is a bunch of plots that are the means of all the 10,000 samples we drew up here. Each sample had 5, and each time the mean was computed for that sample, and we plotted it in this distribution. The mean of this distribution here is 15.99. That almost perfectly reflects the actual population mean of 16. The actual population mean of this population is 16, and the average of all of these sample statistics is 15.99. What we're doing here is we're drawing sample after sample, computing the average, and plotting it down here. Each of these cells, each of these boxes, is representing the average of one of the samples. So like this one right here was a sample of 5 that had an average of 14 rather than 16. This one up here had an average of 18 rather than 16. However, if you take the average of all of them, not every individual sample will be an accurate representation of the population. But on average, the average of all of them is an accurate representation of the population. Notice what happens though with the standard deviation. Without correction, the standard deviation is smaller than the population standard deviation. The population standard deviation is actually 5. That's how far a typical score will fall away from the mean in the population. But the standard deviation in the sample is only 2.26 because this standard deviation was computed not based on the degrees of freedom, not based on n-1. This is a biased statistic. I'm going to show you the same thing in a different way. Instead of computing the mean in a plot down here, I'm going to compute the standard deviation. So, in the first sample, I'm going to draw 5. 1, 2, 3, 4, 5. I'm going to compute the standard deviation from these scores and plot it here. This is a standard deviation of 1, 2, 3, 4. That's how far apart these scores typically fall away from each other. I'm going to compute another sample. 1, 2, 3, 4, 5. Figure out how far away these scores are. The standard deviation here is 4. We've plotted that standard deviation there as 4. I'm going to draw another sample. Of those 5 scores, the standard deviation is 5. We plot that there. If we do this a bunch of times, and each time we compute how far spread are the scores, what's the standard deviation, and we plot it down here, you will see after 10,000 times that the standard deviation of this distribution is 4.2. Right here, 4.2 is the typical distance that scores were spread out in the sample. If we don't correct that computation by dividing by n-1 instead of dividing by n, then we will find that our sample standard deviation underestimates the population variability over and over. But if we divide by n-1, then this value would be 5. The typical distance would be 5 if we computed the standard deviations for each of these using the corrected value of n-1. Let's look at another example that's much simpler. Let's say that we have a population of 9 scores. Oh, sorry, a population of 6 scores. 0, 0, 3, 3, and 9, 9. If I compute the actual mean of this population, this is admittedly a very small population, but if I computed the actual mean of this population, it would be 4. And if I computed the variance, it would be 14. Just trust me on that, okay? Let's draw sample after sample after sample from this small population, where each sample is just 2 scores. In the first sample, we'll draw a 0 and a 0. From this population, we drew that 0 and that 0. In the second sample, we might draw a 0 and a 3. We drew a 0 and a 3. For the third sample, we drew a 0 and a 9. For the fourth, we drew a 3 and a 0, etc., until we have all the possible combinations of samples from the population. Now, if we computed the mean for each of these samples, and then we averaged them all together, we would find that the average mean represents the population mean. because it's an unbiased statistic. Each of the individual sample means will not represent the population mean, but on average they will. So let's take the mean of 0 and 0. It's 0. The mean of 0 and 3 is 1.5. The mean of 0 and 9 is 4.5. And if we do that for all of the samples, then all of the sample means individually will not represent the population mean of 4. But if you take the average of them, if you add them all up to 36 and divide by 9, then it will equal 4. Let's look at the biased measure of variance, where we divide the sum of squares by n rather than n minus 1. If we took 0 and 0 and the average was 0, and we took the deviation of each of these scores from the mean, 0 minus 0 is 0, 0 minus 0 is 0, we square each one, it's still 0, we sum them up, it's still 0, we divide by 2, it's still 0, then the biased variance is 0. Let's do it here. The distance of 0 away from the mean is 1.5, and and the distance of 3 away from the mean is also 1.5, but in the opposite direction. And if we square both of those, 1.5 squared, negative 1.5 squared, add them together, divide by 2, the biased variance is 2.25. If you do the same thing for all of the samples, and you come out with a biased variance, and you add up all the biased variance, you will get 63, and divide that by 9, you will end up with 7. The actual variance is 14. If we compute the unbiased variance for every sample, we take the 0 and 0, compute the variance by n minus 1, we take the 0 and 3, we compute the variance by n minus 1, and we do the same thing for all the samples. In this unbiased variance computation, the variance is estimated at 126 when you sum them all up and divide them by 9 to figure out the average variance, and it's actually 14. Since the actual population variance of this sample is 14, then this, using n minus 1, is an unbiased method of measuring variance. This form of measuring variance, where you don't use n minus 1 and you just use n, comes up with an underestimate of variability, such that our variance is computed as 7 when it's really supposed to be 14. So using the corrected n minus 1 allows us to, in an unbiased fashion, accurately reflect the population standard deviation. A standard deviation describes scores in terms of distance from the mean, how far a score typically is from the mean. You can describe an entire distribution with just two numbers, with just the mean and the standard deviation. And knowing those two things allows you to reconstruct an approximation of the measurement scale or the set of data from just those two numbers. If this were your sample, it's 20 scores, it's got a mean of 36 and a standard deviation of 4, but somebody didn't show you this chart. All they told you was that the mean was 36 and the standard deviation was 4, and that it was approximately normally distributed. You could, in your head, create a curved line in the shape of a normal distribution with a mean at 36 and a standard deviation of 4. And that would allow you to reconstruct the approximate shape, without knowing exactly every score, approximately how this sample of scores would have looked. It has a mean of 36 and a standard deviation of 4. You can also know a couple of important things when scores are normally distributed. Between -1 and +1 standard deviations fall about 70% of scores. If you carry this out to 2 standard deviations above the mean, out here, about 95% of scores fall between 2 standard deviations above and 2 standard deviations below the mean. So almost all of the scores will be somewhere between 36 minus 8 and 36 plus 8. 70% of the scores will fall between 36 minus 4 and 36 plus 4. Most of the scores will fall there, but almost all of them will fall there. Another thing we need to understand is what happens to the standard deviation when you make transformations. We did this with the mean earlier, but if we add a constant to each of the scores, the mean is changed by that same amount, and the standard deviation the standard deviation is actually unchanged. So if you take each of the scores in this distribution and you add 2 to each score, then these 6s become 8s. See down there? These 5s become 7s. See down there? And all the scores shift by 2 if you add 2 to each score. But the spread of the scores, the standard deviation of the scores, remains unchanged. They're still spread out the same amount as they were before. When you multiply each score by a constant, the mean is changed because it's multiplied by that same amount, but the standard deviation is also changed. It's also multiplied by that same constant. So if you take each score and you times it by 2, then this 1 becomes 2, this 2 becomes 4, this 3 becomes 6, and you see them plotted out here. And the typical distance of the scores from the mean doubles as well because the spread of the scores just doubled. The goal of inferential statistics is to detect meaningful and significant patterns in your research results. Variability in the data influences how easy it is to see patterns in the findings. If there's a lot of variability, that can obscure patterns that would be visible in low variability samples. As you can see in panel A here, there's a clear difference in the two samples. The mean of the first is 35, the mean of the second is 40, but it's easy to eyeball and say these scores are clearly lower than these scores. If you had a similar experiment with the same means of 35 and 40, but the variability was so spread out that the scores weren't clustered together, they were really far apart, you couldn't tell easily just by eyeballing how different those two samples are from each other. If I only showed you this graph right here, you would say, I don't know, maybe there's a difference between those two groups, but the spread is so overlapping that it's difficult to tell. In the same way that it's difficult to eyeball this difference, it is difficult for statistics to assess whether there's a difference as well. When we run our inferential statistics later on in the course, we're going to find that in a situation like this, with high variability and a lot of overlap between your two groups, your statistics are going to say, we're uncertain whether this is really a difference. It seems like probably there's not a real difference. But if the scores have low variability and they're clustered together in clean groups like this, your statistics are going to say, yeah, there's a very obvious difference between these two groups. Now, statistics are a more sophisticated and more standardized procedure for going about this same process that we're doing eyeballing here. But basically what I'm saying is the process by which we eyeball these things is very similar to the process by which your statistics are going to see whether there are differences between the two groups, taking into consideration how closely clustered together the scores in those groups are. This idea here is sometimes called error variance. This spread of scores here is called error variance when it's an estimate of how spread out all of the variability is, and how much of the differences, how much of the variability you haven't accounted for because of your two samples or because of your independent variable. This is analogous to static on a radio. If you have like a old style dial radio where you're trying to find a particular station, if you get right on the station, then you can hear clearly, but if you're off by just a little bit, then it becomes fuzzier and fuzzier. And as you get further away from the station, the sound of the fuzziness increases to such an extent that it's difficult to discern the real program amidst all the noise. In that same way, it's difficult to tell whether your treatment had a real effect amidst all this variable noise here in the graph. Before we conclude today, I'd like you to take a moment and practice identifying which of these symbols is associated with each of these concepts. In order to succeed in this course, these symbols are really going to have to become second nature to you. When you see one, you're going to have to know immediately what it means. So take a moment and practice learning. Pause your video, and in a moment, I'll tell you the answers. Here you go.